Let's talk about denotational semantics today, a particular style of defining semantics of programs. And before we actually drill into it, I should point out that I assume that you have studied material on tree-based abstract syntax, that you have looked at basic interpreters, and you also have studied big step operational semantics beforehand. So denotational semantics, another name for it would be functional semantics, because the semantic domains, that is the types essentially used for the meanings in the semantics, these tend to be function types. So for example, for an imperative language, we could use the store transformer type, which maps variable assignments, that is stores, to stores. Which means this is the store before statement execution, and that would be the store after statement execution. And the meaning of an expression would be a store observer. So we would observe the store because there might be variables in the expression, and we would map it to a value. So semantic domains are function types essentially. And the mapping from syntax to semantics, well, these are literally defined as semantic functions. So we are going to have, for an imperative language, we're going to have functions as and e for mapping syntactic statements or syntactic expressions to, well, store transformers or store observers respectively. Now a key point with defining semantic functions in denotational style is that they should be defined compositionally. So let's see what this means. We compare this with operational semantics. So we have two rules here of a big step operational semantics. The rule for sequential composition of statements and the rule for while loops. It turns out that the rule for sequential composition is what you might call compositional. Compositionality, though, is violated by the rule for while loops. So compositionality means that you define the meaning of a construct solely in terms of the meanings of the constituents. So this is what we do here. We define the meaning of sequential composition S1, S2 in terms of the meaning of S1 and the meaning of S2. So this is compositional. However, here we define the meaning of a while loop with a condition E and a loop body S. We define it not in terms of the meaning of E and S. Rather, we define it in terms of the meaning of some compound expression, well, statement, which happens to include the same while loop again. So this is not compositional. So why is compositionality important? Well, it's pretty much the same story as for, let's say, primitive recursion versus general recursion. If you have compositionality, your semantics is just better structured. It's more obvious that you actually define a mapping from syntax to semantic domains. So we're going to stick to the principle of compositionality from here on. So here's how we set up a compositional scheme for the semantic functions S and E. So just to remind you, these are our semantic domains: store transformers, store observers. We're going to define functions S and E, mapping statements and expressions to store transformers and observers. And we use these so-called Oxford brackets here just to make clear where we deal with syntax as opposed to semantic domains. So we have equations defining the functions S and E, and there's basically one equation per syntactic construct. And on the right-hand side of the equations, we assume semantic combinators. So we still have to define them, but we just give them pretty much the same name as we use for the constructor of the abstract syntactical pattern. So we underline them to distinguish them from the constructor names. And as you see, we apply these semantic combinators just directly to the recursively mapped constituents of the constructs. So for example, here we have seek. The meaning of a sequential composition is defined by the semantic combinator seek and applied to the semantic meanings of the two statements composed by seek. Or here for while, the semantic meaning of while loop is the application of the semantic combinator while to the meaning of the condition E and the meaning of the body S. And this is just the same scheme all over. It's just a scheme. We haven't really yet defined precisely what the meaning is, because that's up to the semantic combinators that we still need to define. So basically these semantic combinators only see meanings. They don't see any syntax anymore. All right, so just for clarity, these are obviously the types of the semantic combinators involved. I mean, these types just follow directly from what we have seen here. So for example, skip. Skip is the combinator for an empty statement. It's just a trivial store transformer, presumably. Or seek. Seek takes two store transformers, namely two meanings for the statements being sequentially composed, and it constructs another store transformer from it. Here, the while combinator, it takes a meaning for a condition and a meaning for a statement, that is the body of the while loop, and it constructs another meaning for a statement. The others are likewise. Now let's try to define some of these semantic combinators. So for now we just use a semi-formal style of definition, but it should be pretty clear what we mean here. So for example, the skip combinator, which assigns a meaning to the empty statement. An empty statement obviously doesn't change the variable assignment. Sequential composition, it takes two meanings, f and g, and a store, and it applies basically the first meaning corresponding to the first statement in the sequential composition to the incoming store, thereby computing another store, which is then passed to the second meaning g, corresponding to the second statement in the sequential composition. Here we have the meaning of assignment. So essentially we have to update the incoming store in the position x to now assume the value as computed for the right-hand side expression. So we use the meaning f for the right-hand side and we apply it to the incoming store, because there might be variables in the right-hand side expression. And here's also the meaning of a if statement. Well, if the condition evaluates to true, then we apply the meaning of the then branch to the store. Otherwise, we apply the for false, we apply the meaning of the else branch to the store. And it might also be that maybe the meaning of the condition is not defined. Well, then the meaning of the if statement is also not defined. So, I mean, likewise, we can define meanings of all the expression forms, and that's pretty straightforward. The only interesting case is, of course, while. So what is the definition of the semantic combinator while? Because that was obviously also the challenge with the operational semantics. We didn't have a compositional style there for the semantics of a while loop. And that's going to be a little bit tricky. Okay, so we just start from a clever assumption. We just assume that we would already know the definition of while. So let's say while applied to f and g, f being the meaning of the condition, g being the meaning of the body. Let's say it's t. Well, if it would be t, then we could reasonably assume that t should be equivalent to this application of the semantic combinators if, seek, and skip. So basically we say we can also take if, apply it to the meaning of the condition, and for the meaning of the then branch, then we assume the sequential composition of well, the meaning of the body of the while loop, and again the entire while loop. And for the else branch, we assume the meaning of the empty statement. So the important thing here is we are talking about meanings, we are talking about semantic combinators. We are not talking about syntax here, even though, of course, this looks very suggestive. So if we had T already, if we had the meaning of the while loop already, then we would also be able to express this meaning in this different form. So now what we can do is we can just parameterize in T. So we define a function h, we parameterize it in T, and we just define it as before, as above here. And now we just consider a progression of applications of h, where we apply h initially to the undefined meaning, and then we apply h to the application of h to the undefined meaning. So we basically consider the progression of the repeated application of h to the undefined meaning. And that's interesting, because if we, in a way, if we take a limit of this progression here, well, then we have found the meaning of the while loop. So the meaning of the while loop is indeed essentially the fixed point of this function here that we have just defined. And for what it matters here, we can define the fixed point of a function k simply by saying, okay, the fixed point of k is k applied to the fixed point of k. So this is, in a way, a definitional property of a fixed point. So in order for something to be a fixed point of k, of course, k applied to that fixed point should be equal to the fixed point. It turns out that we can kind of use this definitional property in a, well, definitional sense, giving us effectively a way to compute the fixed point. We will see this when we map this to Haskell. But anyway, so the while combinator is defined as a fixed point over a function that essentially uses the if, seek, and skip semantic combinators. Now, for this to be sound in a mathematical sense, we would need to make certain assumptions about semantic domains and the semantic combinators. We would basically need to meet constraints explained in detail by domain theory. So in essence, we cannot assume that we operate on naive sets and on plain functions here, but rather we would need to operate on appropriately constrained algebraic structures here. But we skip this here because we want to sort of focus on the intuitive aspects of denotational semantics here, in particular compositionality. Okay, so now let's map the denotational semantics to Haskell, and we get an interpreter pretty much immediately. So this is how we imagine to use the interpreter. So this could be some program for Euclidean division, and we provide it with some input store or variable assignment. So operands for Euclidean division would be 14 and 4. So we execute this program with this store, and execute would be like our semantic function, what we called S previously, and this returns some resulting store. So the quotient would be 3, the remainder would be 2, and x and y would still be bound to the arguments as in the beginning. So for such a denotational interpreter, we would need to map the abstract syntax. That's pretty straightforward. We would need to map the semantic domains, the semantic functions, and the semantic combinators, and of course also the fixed point combinator that we assumed. So here are the semantic domains and the semantic functions. So we have as values for expressions, we've got a sum over int and bool. Stores are just maps as a data structure here from strings to values. Store transformers are functions on stores, and store observers are functions from stores to values. So this is the semantic function mapping statements to store transformers, and these equations here, they just follow very closely what we have seen earlier in our semi-formal notation. So we assume semantic combinators assign, skip, assign, seek, if, while, prime. So we just prime them to avoid any sort of name clashes. And you see we adhere to the compositional scheme by applying the semantic combinators indeed to the recursively processed syntactic components. So here are the semantic combinators. This is the skip prime combinator. This is the meaning of an empty statement. Well, it's just the identity function, so we map a store to itself. This is the assign prime combinator, the meaning of an assignment. Well, what we do is we basically update the store m in the position x to now return f of m, which is the value of the right-hand side. This is the semantic combinator seek prime. It's for the meaning of a sequential composition. Well, and it's essentially just the flipped functional composition. This is the semantic meaning or the semantic combinator for if statements. Essentially, we just translate it to an if expression of the host language. Well, and here we've got the while prime combinator, and we just do the very same as in our semi-formal development. We apply the fixed point combinator to a function h, and the function h is parameterized in t, presumably the meaning of a while loop, and we apply semantic combinators if prime, seek prime, skip prime in right the same way here to form the semantic meaning of a while loop, assuming that t is that semantic meaning. And here down here we have the fixed point combinator, and so as we see, it's a polymorphic function which can take any function from a to a and returns an a, and we just use the definitional property as we discussed earlier. So in order to, let's say, compute the fixed point of f, we just apply f to the computation of the fixed point of f. And in the cases where such a fixed point is indeed defined, we will effectively compute it that way. That's it. All the code for our treatment of denotational semantics is in a YAS repository. And the topic of denotational semantics is discussed in more detail in a corresponding chapter in the software languages book. There we also add some details related to a more sophisticated style of denotational semantics, the so-called continuation style. And we also apply denotational semantics to program analysis by abstract interpretation. Thank you.